Today, we're going to be talking about transient analysis with regards to parallel RLC circuits. So I handed out a handout to you all. It's a big table, and this table is effectively going to be I say effectively, it is actually your equation sheet for exam 2. Just as a heads up, I also uploaded the equation sheet for exam 1 onto Canvas, I believe, earlier today, so you guys have access to that. So I've made this table for you all so that you can use it while you're doing your homework and all of that kind of good stuff as well, so that hopefully after today's class meeting, we never really have to think about the calculus that's related to what we're going to be doing here ever again. That's what the table is for, so that you don't have to worry about how to remember to do the derivatives of big ugly things and this, that, and the other. It's all done for you on the table. All right. So transient analysis of RLC circuits is going to be very similar to transient analysis of RL circuits and RC circuits, except that now we're going to be dealing with second order differential equations. Okay. So let me write this down. Total response of parallel RLC circuits. Okay. So let's say that I have the following circuit, wherein I have a current source sourcing some amount of current IS, like so. I'm going to give myself a resistor over here. I am intentionally not labeling it because it's literally just going to be a path for our current to take once I disconnect my source. So it's not actually important to the RLC network side of things. I'm going to have a switch here. Don't know why my program is giving me a ton of lag today. I've updated my computer, so here we're going to have some resistance R in parallel with some inductance L in parallel with some capacitance C. Because all three of our elements are connected in parallel, they're all going to have the same voltage drop across them. So I'm just going to call this voltage V. But remember, because this is the voltage drop across a capacitor, it cannot change abruptly. So our same basic rules apply. I'm going to define this current here as my resistor current as a function of time, IR. This will be my inductor current as a function of time, IL. And this will be my capacitor current as a function of time, IC. And for this particular example where we're deriving everything, we're going to be dealing with a natural response system. So I'm going to be disconnecting my current source from my network. So at t is equal to 0 minus, our switch was closed. And we should see that all of our source current IS is flowing through our inductor, which would be represented by a short circuit because it would be a DC circuit. And so our inductor would have some amount of stored energy. The voltage drop across our inductor would be 0, which means the capacitor would not have any stored energy. And then once our switch opens up, we should see that the energy that is stored in the inductor, some portion of it will be transferred to the capacitor, some other portion of it will be absorbed by the resistor and converted into heat. And we'll see that energy kind of ping-pongs back and forth between the capacitor and the inductor until the resistor manages to convert everything into heat, at which point everything is falling. Okay. So we are going to mathematically describe what those transfer relationships look like today. Okay. So during the transient condition, And so for this, I mean t greater than or equal to 0 plus. We can apply Kirchhoff's current law at the top node of our parallel RLC circuit, and we'll find that our resistor current IR plus our inductor current IL plus our capacitor current IC must all add together and equal to 0. And now I am going to use relationships to express all three of those currents in terms of the voltage V, which is common to all three of those elements, right? So Ohm's law tells me that the current IR is going to be 1 over R times V of t. Then I have my inductor, which should be an integral-based relationship, right? So that'll be 1 over L times the integral from some time t naught to some later time t of V of t prime dt prime plus my inductor current at t naught. And then I have my capacitor current, which is a derivative-based relationship. So we'll have C dV by dt is equal to 0. So this is what's known as an integral differential equation. And I don't know about you guys, but I don't like integral differential equations because they're annoying. So what I'm going to do to make this a little bit easier on us is I'm going to take the derivative of both sides of this equation to get rid of that integral, and it will leave me with a second order differential equation, okay? So the derivative of our first term, actually, I'm going to rearrange things as well very slightly. So I'm going to take the derivative of this term first so that I'll have my second derivative thing being my first expression, then my first derivative, and then my zeroth derivative thing, so that it's in a nice, neat form. So taking the derivative of both sides of this expression is going to leave me with C times the second derivative of my voltage with respect to time plus 1 over R times the first derivative of my voltage with respect to time plus 1 over L times what I like to call the zeroth derivative of our voltage with respect to time, which is nothing more than the voltage itself. And the derivative of this constant initial condition on our inductor current is going to be 0. So it goes away. And now what I'm going to do is I'm going to divide both sides of this equation by C such that the coefficient on my second derivative term is 1. Okay. So now I will have the second derivative of my voltage with respect to time plus 1 over RC times the first derivative of my voltage with respect to time plus 1 over LC times my voltage is equal to 0. And so I have a nice, neat, homogeneous second order differential equation. Okay. In a couple of days, we're going to come back to this relationship, so that's why I'm putting a box around it. All right, so now we need to solve this second order differential equation. And I don't know how many of you have had Math 245 yet, so I'm going to assume that none of you have. And we are going to solve it effectively in the exact same way that we solved our first order differential equation way back in circuits 1. I need a function whose first and second derivatives look like the same thing as the function itself, which is very obviously an exponential function. Okay. So I am going to guess that the solution to this will be of the form V of t is equal to A e to the st. This is literally the exact same guess that we used way back in circuits 1 when we were setting up things up for first order transient. So I'm going to substitute this guess back into my differential equation. What's the second derivative of this going to look like? Yeah, so s squared ae to the st. Then I'm going to have plus 1 over RC times S AE to the ST plus 1 over LC times AE to the ST is equal to 0. And I can see that I have some common factors in here. So I'm going to pull the A out over here on the left. And I'm going to pull the E to the ST out and put it over here on the right. And so what I'm left with in the middle is S squared plus 1 over RC times S plus 1 over LC. This is my characteristic polynomial for this system. Because I have two energy storage elements that can't be combined to look like a single energy storage element, I wind up with a second order polynomial equation, also known as a quadratic function. And so I'm going to use good old 8th grade math to figure out what the roots of that quadratic function is, right? So for those of you that don't remember the quadratic equation, S is going to have two values or two roots. So I'm going to have negative b, where b is the coefficient on my first order term. So that's going to be negative 1 over RC. Plus the square root of that term b squared. So that'll be 1 over RC squared minus 4 times a, which is the coefficient of our s squared term, which is 1, so just 4 times 1, times c, which is the constant term in our expression. All of this is going to be divided by 2a. And now I'm going to play around with things a little bit here. And by that, I mean, I'm just going to move this 2 from the denominator up into the numerator so that I don't have fractions on top of things. Okay. So I will have S1 comma 2 is going to be equal to negative 1 over twice RC plus the square root of 1 over twice RC squared minus 1 over the square root of LC squared. So I got a little bit fancy there at the end. So when I bring this 2 up here and then move it inside, it's going to look like 4 over 4. So that's why I don't have a coefficient out here. And then I'm explicitly splitting up this 1 over LC into 1 over the square root of LC squared for reasons that you'll see in just a moment. Okay? So each of these parts of this equation have special names. So we are going to define a term alpha to be 1 over twice RC. Alpha is what's known as the Neper frequency, measured in Nepers per second, where a Neper is just a dimensionless quantity that tells us how quickly this signal is going to decay as a function of time. So it's similar to, but not the same thing as the time constants that we saw in first order RL and RC circuits. Isaiah, I believe you raised your hand a moment ago.
How come we don't have to have that?
You are, because I made a mistake. Thank you. You're 100% correct. Thank you for that. So like I said, our Neper frequency is related to how quickly our signals are going to exponentially decay in a second order circuit. So not the same thing as a time constant, but playing a very similar role, telling us about the rate of decay in our system. Okay. We are going to define another constant, omega naught, as 1 over the square root of LC. This is what's known as the resonant frequency of the circuit. And it is measured in radians per second, where radians is a dimensionless quantity as well, so that it's okay that I'm combining Neper frequency and resonant frequency here. It's still just going to come out as something measured in per second. Okay. Have any of you guys ever heard of the term resonant frequency before? Hayden, where did you hear about resonant frequency? I don't remember. Anybody remember where they heard about resonant frequency? Physics in high school. Okay, so can you tell me a little bit about what you know about a resonant frequency, Walker?
I know that everything vibrates at a different frequency. If you do it at a certain time with that frequency, then eventually the things start to break down.
Absolutely fantastic answer there. So that's usually one of the examples that I give is talking about the Tacoma Narrows Bridge, which Walker may have been referencing there. That was a bridge that was developed in the middle of the 1900s. And the resonant frequency of the bridge was low enough to where when wind started blowing against the bridge, it caused the frequency, or excuse me, caused the bridge to resonate or oscillate at its resonant frequency. And we saw that the bridge literally shook itself apart. So from an electrical engineering perspective, resonant frequency is the frequency at which the impedance of this system is going to look purely real, meaning that any positive reactance contributed by our inductance is going to be exactly counteracted by any negative reactance contributed by our capacitor. When we get into circuit 3, we'll take a very long look at resonant circuits and how they're used and all of that kind of good stuff. But for now, we are just going to say omega naught is equal to 1 over the square root of LC, and we're calling it the resonant frequency. Okay, Hojun.
It's all the circuit is going to
So that's a fantastic question as well, and it depends on what we want. So let me explain what I mean by that. Okay, so for a circuit to be undergoing resonance, it means that we are getting the maximum possible output for the smallest possible input into the system. So if we're trying to develop a resonator, that's a really good thing because it means that we are going to get effectively sinusoidal excitation by putting practically no energy into the system. It's just going to ring out continuously, which is fantastic for clock circuits and things like that. That being said, if we were trying to develop a circuit that was going to be part of a control system for something like an airbag or something like that, resonance would be really, really bad because it would be very easy to accidentally set off our airbag due to a very small perturbation. We would want a system that was actually underdamped, and we'll talk about what that means here in a minute, to where effectively it's slow to respond so that we don't accidentally trigger things. Okay. Very, very good questions today. All right. So in terms of our Neper frequency and our resonant frequency, we can then define S1 and 2. So we could say that S1 is going to be negative alpha plus the square root of alpha squared minus omega naught squared. And S2 will be negative alpha minus the square root of alpha squared minus omega naught squared. So S1 is always going to be the one with the positive sign in the middle. S2 is always going to be the one with a negative sign in the middle. So we have two distinct frequencies here, S1 and S2, which means realistically, we actually also have to have two coefficients for A, right? We can't satisfy both things with a single coefficient. So our voltage V of t is generically going to be of the form A1 e to the S1t plus A2 e to the S2t. You can think about this in terms of superposition. So if we excited the circuit at one resonant frequency, we'll get one value of A1. If we excite it at a separate thing, we're going to get the second resonant frequency, which needs its own corresponding initial condition to take care of that. Okay. So this is our generic equation. We'll circle back to this in a moment, but we do actually have a little bit of a problem. Okay. So before we get into that problem, I want to define this response to be the response of what's called an overdamped circuit. Okay. So this is our overdamped response. And this is what our voltage signal will look like for any system in which alpha is greater than omega naught. So we can see here, looking at this expression, that we can choose what value of R, C, and L we have. So it's possible for us to have instances where alpha is greater than omega naught, alpha is equal to omega naught, and alpha is less than omega naught. And so we're going to have to think through the implications of all three of those things, okay? So when alpha is greater than omega naught, I have a negative number plus the square root of some smaller positive number, right? So that means that S1 is going to be negative and real, and S2 is also going to be negative and real. Okay? So S1 and S2 are negative and real numbers. Okay. Now, let's introduce what a critically damped system would look like. And then I'll give you the response equation here in a moment. So critically damped response is when alpha is exactly equal to omega naught. Okay. So when alpha is exactly equal to omega naught, S1 is equal to S2 is equal to negative alpha. So if we look at our response equation here, we run into a little bit of a problem inasmuch as if this number S1 is equal to this number S2, it seems like I should just be able to add these two relationships together and get a single expression, right? So it would be just whatever A1 is plus whatever A2 is, and we could call that just A. The problem with that is that we are going to have two initial conditions on our system because we have two energy storage elements, a capacitor and an inductor. So we have to modify our equation to be able to account for the separate initial conditions that we are going to have. So in a critically damped circuit, we will see that our voltage waveform will actually take the following shape. A1 times T e to the negative alpha t plus A2 e to the negative alpha t. So it's still the same generic form. It's a sum of exponential functions, but now we have this t here as well, which is required of us because we have repeated roots for our differential equation. Okay. The last situation that we might have is an underdamped system. And in an underdamped system, alpha is less than omega naught. So let's look at what happens when alpha is less than omega naught, okay? So we have negative alpha plus the square root of alpha squared minus omega naught squared. If alpha is less than omega naught, is alpha squared minus omega naught squared going to be a positive number or a negative number? Negative number. So we have a negative number plus an imaginary number. So we're going to have a complex number in total. And we can see, because we have a plus sign here and a minus sign here, that S1 and S2 are going to be complex conjugates of each other, right? So S1 is equal to the complex conjugate of S2. So when we have the sum of two exponential functions where S1 and S2 are complex conjugates of each other, we can wind up using Euler's identity, which relates sine and cosine functions to complex numbers in order to get the relationship V of t will be equal to B1 cosine omega dt plus B2 sine omega dt. All of this is multiplied by e to the negative alpha t. Okay? And we're going to define omega d to be the square root of omega naught squared minus alpha squared. Okay. Yes.
What would you want all of that multiplied by
E to the negative alpha t. Now, I see you're a bit far away, so this is hard to read. So let me show you a little something here really quickly. I'm going to open a file. Let's go to Dropbox. Circuits 2. Here, maybe. Open the folder. All I'm doing is opening up the table that I literally gave you. We have the relationship for overdamped response up here. A1 e to the S1t plus A2 e to the S2t. We also have plus y at infinity. So this y at infinity bit is what's going to happen when we have a source being added into the circuit versus taken out of the circuit, how we derive things. Right here, I have y is equal to A1t e to the negative alpha t plus A2 e to the negative alpha t. Maybe I can make this slightly bigger. Yeah. I didn't want to highlight everything there. And then down here, I have my underdamped response, and I also provided you with the definition of omega d. So literally every equation that we came up with here a moment ago is on the table that I've provided to you. On the table, I have also provided you with the derivative of our response relationships, right? So that you don't have to take the derivative of this thing yourself when we use these in order to actually analyze our circuits and come up with what our responses are going to look like, which we'll do here in a moment. As a heads up, the table also includes information for series RLC circuits. So effectively, we can see from the jump here that alpha is 1 over 2 RC, which is what we derived for a parallel RLC circuit. It's going to have a different value for series RLC circuit, R over 2L, which we'll see On Wednesday, we get back from break because we're taking our test on Monday. The resonant frequency is the same for both parallel circuits, parallel RLC circuits and series RLC circuits. So we're going to use this table very extensively, starting, let's say now. Okay. So let's analyze the circuit and figure out how to use this table to do things. Okay. So I might be doing things in a very slightly different order than I'm asking you to do on your homework assignments because I can't exactly remember the order I asked you to do things on the homework assignments, but we'll talk about it in a moment. So I'm gonna make up a circuit here. So let's say that I have the following circuit. Let's make this a 10-volt source. Connected to a 5 ohm resistor. And let's have a switch that's going to close at T is equal to 0. Let's put a 10 ohm resistor here. Let's make this 1 millihenry. And let's make this 1 microfarad. I'm going to define this as my voltage V of T. This will be our capacitor current, IC of T. This will be our inductor current, IL of T. And let's say that we are interested in finding IL of T and V of T for this particular circuit. So the first thing that we are going to do is we are going to analyze this circuit at T is equal to 0 minus. And we are going to solve for these 3 pieces of information. These are going to be the critical things. Okay. So at T is equal to 0 minus, our switch is open. So we are going to have the following circuit. We have our 10-volt source in parallel with a 5 ohm resistor. The open circuit right here is representing our switch. Here's my 10 ohm resistor. This short circuit is representing my inductor. This open circuit over here is representing my capacitor. So this will be the voltage V at 0 minus. This will be the current IC at 0 minus. This will be the current IL at 0 minus. Who can tell me what the values of these quantities are? They're all 0. Absolutely correct. So effectively, our RLC network isn't connected, so all of these should be 0. Another way to think about things, just for the sake of argument, quite obviously, IC is equal to 0 because it's the current flowing through an open circuit. Hopefully, quite obviously, the voltage V at 0 minus is going to be 0 because it's the voltage drop across a short circuit. So really then we only need to figure out what IL at 0 minus is because it's the only thing that might not be 0. And Kirchhoff's current law at this node will tell us that it has to be 0 as well if we didn't believe it was all 0 by inspection. So let me write those down. So V at 0 minus was 0 volts. IL at 0 minus was 0 amps. And IC at 0 minus was also 0 amps, excuse me. Right. So there's our analysis at T is equal to 0 minus. This was fairly easy and straightforward. Any questions? All right. Now we're going to analyze our circuit at T is equal to 0 plus. So at T is equal to 0 plus, our switch is going to be closed. Okay? So I'm going to have my 10-volt source like so. Here's my 5 ohm resistor. My switch is going to be closed. Here's my 10 ohm resistor. I'm going to represent my inductor as if it were an open circuit. And my capacitor as if it were a short circuit. Somebody tell me why. Absolutely right. So since my voltage across my capacitor was 0 volts, I need to replace my capacitor with a 0 volt source, which is just a short circuit, because the current flowing through my inductor was 0 amps. I'm replacing it with a 0 amp source, which is just an open circuit. Absolutely right. So just to define things clearly here, here's V at 0 plus. Here's IC at 0 plus. Here's IL at 0 plus. And we know that the voltage drop across the capacitor cannot change. So whatever value it had at 0 minus, it must continue to have at 0 plus. So we have 0 volts. The current flowing through an inductor cannot change abruptly. So IL at 0 plus must be equal to IL at 0 minus, must be 0 amps. The current flowing through a capacitor can change. So what do we expect that current to be? 1 amp. 10 volts divided by 10 ohms is equal to 1 amp. Absolutely right. Okay. Now we are going to analyze the circuit at T is equal to infinity. So at T is equal to infinity, our switch is closed, but we are back at DC steady state, which means we're going to represent our inductor by a short circuit and our capacitor by an open circuit. So that means we should have the following circuit. So here's our 10-volt source. In parallel with our 5 ohm resistor. Here is our 10 ohm resistor. My inductor is being replaced by a short circuit. My capacitor is being replaced by an open circuit. This current will be my inductor current at infinity. This current will be my capacitor current at infinity. And this will be my voltage at infinity. So what should my voltage at infinity be? Zero volts, because it's still the voltage drop across the inductor, which is being represented by a short circuit, and the voltage drop across the short circuit is always 0 volts. What value will my inductor current have? 1 amp. 10 volts over 10 ohms is equal to 1 amp. Absolutely. And lastly, what value must my capacitor current have? 0, because it's the current flowing through an open circuit. Absolutely. All right. So we've analyzed our circuit at t is equal to 0 minus, t is equal to 0 plus, and t is equal to infinity. So now what we're going to do is figure out, based on these component values, whether this circuit is a overdamped circuit, an underdamped circuit, or a critically damped circuit. Okay. So in order to do that, hopefully pretty obviously, L is 1 millihenry and C is 1 microfarad, because it's literally the only inductor and capacitor in the circuit. We need to figure out how to find the equivalent resistance, right? So our equivalent resistance, just like we had in our first order circuits back in circuits 1, is going to be the Thevenin resistance seen looking into the terminals of our energy storage elements. But in this case, we have 2 energy storage elements. Luckily for us, they're in parallel. So we're just going to open circuit the capacitor and the inductor and look in with the voltage source turned off. Okay. So let me just write here, finding REQ. So our voltage source is turned off. Here's our 5 ohm resistor. Here's our 10 ohm resistor. We've taken out our inductance. We've also taken out our capacitance. And we're looking in to the terminals of our energy storage elements. What do we see? I've heard 15 and I've heard 10. Which is it? It's just 10. Because our off voltage source shorts out the 5 ohm resistance. So the only resistance that's going to contribute during the transient condition is the 10 ohm resistor. So REQ is equal to 10 ohms. So then we have alpha is equal to 1 over twice REQ times C. So let me grab a calculator real quick and figure that out. So 1 over 2 times 10 times 1 times 10 to the minus 6, I believe, because I'm dealing with a microfarad. Yep. I get alpha of 50,000. Nepers per second. Omega naught is the square root of 1 over LC. So that's the square root of 1 divided by 1 times 10 to the minus 3 multiplied by 1 times 10 to the minus 6. And I get 31,622 and some change. Let's call it 623. Hold on. 31,622.777 radians per second. I'm going to store these in my calculator and you'll see why in a moment. So I'm going to store that first one as A and the second one as B. And I'm going to make a note of that out here. So based on these results, is this circuit critically damped, overdamped, or underdamped? It's overdamped because alpha is greater than omega naught. Okay. So since our circuit is overdamped, we are going to use our overdamped response relationship. Okay. So now we need to figure out what the most efficient way to solve for things is. Okay. So this process is always going to be setting up a system of two equations, okay? And we are going to wind up using either the voltage drop across the capacitor and the current flowing through the capacitor, or the current flowing through the inductor and the voltage drop across the inductor. So that we're always going to have one relationship and then something else that's the derivative of that previous relationship. Since we are finding our inductor current and our voltage, which happens to be our inductor voltage as well, I'm going to let y of t be this IL, and the derivative of y of t will be related to v. Okay. So if instead we were trying to find the capacitor voltage and the capacitor current, v of t would have been y of t, and the capacitor current would have been related to the derivative. Okay, so we have to know which one is which in order to sort things out. All right, so let me go down here. And actually, let me write overdamped. Okay, so because we have an overdamped circuit, we're going to wind up needing to know what S1 and S2 are. So I'm going to go ahead and take care of those things now, right? So S1 is by definition negative alpha plus the square root of alpha squared minus omega naught squared. Since I have all of that already in my calculator, that's going to look like negative A minus the square root of A squared. Thank you. Right there, plus square root of A squared minus B squared. I get that to be negative 270.167 units of per second. And I'm going to store this in my calculator as C, because we'll use it in a moment. S2 is negative alpha minus the square root of alpha squared minus omega naught squared. So I'm just going to modify that equation really quickly. And I'm going to store this as D. And I got negative 88,729.833 per second. All right. So now we're going to use our table. So we're going to say that V of t is equal to A1 e to the S1t plus A2 e to the S2t plus V at infinity. At t is equal to 0 plus, this becomes V at 0 plus is equal to A1 plus A2 plus V at infinity. Since e to the 0 is 1, our exponential terms wind up going away. So what was V at, yes?
We're doing Y is, IL.
You're right. Let's do that. Let's fix that. Thank you. I just had a brain fart. IL. 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 Thank you for that. All right, so what was IL at 0 plus? 0, okay, what was IL at infinity? Positive 1, okay? So that means we're gonna have the equation A1 plus A2 is equal to -1/8. Everybody okay? All right. Using our table, we can say that V is L times DI by dt, which is going to be L multiplied by, and now I'm going to look at the derivative of Y in my table. So I'm going to have S1 A1 e to the S1t plus S2 A2 e to the S2t, like so. At t is equal to 0 plus, this is going to reduce to V at 0 plus will be equal to L times S1 A1 plus S2 A2. What was V at 0 plus? 0, okay. So now we're just going to have L times S1. So that was 1 times 10 to the minus 3 times what I have stored in my calculator as C, if I'm not mistaken. Negative 11.270 and some change. A1. L times S2, so that's 1 times 10 to the minus 3 times what I have stored in my calculator as D. Minus 88.7298, so let's call that 730. A2 is equal to 0 volts. So I have one equation here, the second equation here, and now I should be able to solve for the coefficients A1 and A2, right? So let's throw this into our system solver. We have a 2x2 system. So the coefficient for A1 in my first equation is 1. The coefficient for A2 in my first equation is 1. And my constant term is -1. My coefficient for A1 in my second equation is going to be 1 times 10 to the minus 3 times what I have stored as C so that I can use exact values. My coefficient for A2 is 1 times 10 to the minus 3 times what I have stored in my calculator is D. And then my constant term is 0. And solving this system, I get A1 is equal to negative 1.14549. I'll just leave it as that. Amps. And A2 is equal to positive 0.145 amps. And from here, I can say that IL of T is going to be negative 1.145 e to the negative. Let me scroll up here to figure out what S1 was. 11,270. Point 166 T plus 0.145 e to the S2 negative 88,729.833 P plus whatever IL was at infinity, which was 1 amp. To find my inductor voltage, V of T, I'm simply going to substitute in the value that I got for A1 and the value that I got for A2 into this expression, right? So my first coefficient is going to be L times S1 times A1. So that's 1 times 10 to the minus 3 times S1, which I have stored in my calculator as C, times A1, which is stored in my calculator as X. And I get 12.9099. So let's call that 12.910 e to the negative 11,270.166 T. My second coefficient for my voltage expression is going to be L times S2 times A2. So that's 1 times 10 to the minus 3 multiplied by what I have in my calculator as V times what I have in my calculator as Y, which comes out to be negative 12.910 e to the negative 88,729.833 T volts. Yes, Toby.
The interior plug computer, that's probably set to the as a.
Right.
That wasn't the case.
So it won't change the units at all. So I technically used L in my expression, 1 times 10 to the minus 3. So let's look at things here just really quickly to figure out what the units for different things are going to be. Okay, so if we scroll up here, it should be fairly obvious that A1 and A2 both have to have units of amps because A1 plus A2 plus a current has the equal current, right? When we look down here, we have L times S1 times A1. All right, so L is inductance. Inductance is measured in henries, where a henry is, if I'm not mistaken, a volt second per ampere, right? So if L is in volt seconds per ampere, we're multiplying by S, which is measured in per seconds, which means we're left with volts per ampere, multiplying by A1, which is in amps, it gives us units of volts. So everything is going to work out correctly if we're paying attention to the units, which means I don't pay attention to the units because they all just work out fine. Yeah. So yeah, so A1 and A2 will have units of amps and everything else comes out correctly because we're using the correct relationships and all of that kind of good stuff. Now you are correct that in our system solver, because this was set equal to 0, we could have just as easily divided both sides by L and just used for our second equation, S1 times A1 plus S2 times A2 is equal to 0, and we will get the exact same result. If V at 0 plus wasn't 0, we would actually have to, like the L would be important in our system solver, which is I think what you were also getting. All right, so we've done a bunch of math and we have a result. That's all fine and great, but how the hell do we know if we did it right? Because this is our first time doing it. This is where LT Spice is going to come. Okay. So I'm going to open up LT Spice and I'm going to build this circuit. I'm only going to build the circuit for T greater than 0 plus. Okay. Largely because I'm too lazy to figure out how switches work in LT Spice. They're there, but it's a pain in the ass and I don't want to do it. So during the transient condition, my circuit is going to look something like this. So I have my 10-volt voltage source. And I'm going to connect that in parallel to a resistor. I'll put the resistor in a moment. Then I'm going to have a resistor across the top here. This branch is going to be for my inductance. This branch over here is going to be for my capacitance. So let's see, I need a 5 ohm resistor right here. A 10 ohm resistor right here. A 1 millihenry inductor right there. So I'm using M to indicate millihenries. And why is my touchpad stop? There we go. Here's my capacitor over here. Just move this thing over. This is 1 micro, so I'm going to put in 1 U, and that'll interpret that as a microfarad. All right, so because we're using LT Spice and LT Spice does everything with effectively nodal analysis, we need to choose. I, typically speaking, always choose ground to be the negative polarity terminal of my capacitor. And that'll work fine for us and for the next almost a month because of the Christmas break and all that kind of stuff, until we hit circuits that have multiple capacitors, and then we'll cross that bridge when we get there, okay? So I'm going to choose ground to be this bottom node, because that's the negative polarity terminal of my capacitor voltage. LT Spice can be a little funky sometimes, so I always choose to use a little stub of wire to connect my ground to, just because in a couple of very rare instances, connecting the ground node to this whole bottom rail just gave me weird results. So I always choose to put in a little bitty piece of wire there. And I am going to label the positive polarity terminal of my capacitor as a voltage VC. So I'm going to put that here. Yes.
How do you put
The letter U. That's it. Literally just 1 and then lowercase u. All right, so I need to include the initial conditions on my capacitor voltage and my inductor current. So I've opened up the Spice command menu. So that's the thing that says .op up here. I clicked on that. And I'm going to put in .ic. It doesn't have to be uppercase, but I'm just used to doing it that way. V, open parentheses, VC. So I'm saying the voltage at node VC has an initial condition of 0 because it was 0 volts. And then I'm going to press Control M to give me a second line. And now I'm going to put in the initial condition on my capacitor current. So that's going to look like .ic I open parentheses L1. So the current flowing through element L1 was equal to 0 at t is equal to 0. And then because S1 and S2 are so large, I probably don't need to run this simulation for more than probably microseconds. Let's start with microseconds and see if that's will come out okay. So let's go to edit simulation command and let's make this stop at 10 microseconds. And if we need to change things, we can change things. Okay. So I'm going to run the simulation. And what I am going to do is I'm going to right click on this plot and I'm going to add a separate plot plane so that we don't have things that are too busy. So I'm going to put the voltage drop across the inductor on one of them and the current flowing through the inductor on the other plot plane. So let's do the top plot plane as the current flowing through my inductor. So that's definitely not enough time because it's not settling to anything. So I'm going to modify that transient thing here. So instead of having 10 microseconds, let's try maybe 10 milliseconds. So that was way too much. And the reason why I'm saying it was way too much is because it hits its final value at less than 1 millisecond and then stays constant. So like 90% of this graph is boring and flat. So let's look at maybe 0.8 milliseconds as our ending point. All right, so that looks like an okay thing. We can see the response. I'll change the colors here in a moment. In the bottom plot plane, so to make it plot on the bottom, I just click on the bottom plane so that that's the one that's highlighted. And then now I am going to click this voltage VC. And so that's what my capacitor voltage is going to look like. So if I right click into the plot plane and I click the add plot plane button, it gives me another one. Yep. Okay, so now we've plotted things in LT-Spice. Now let's talk about how we can verify our results. So I'm going to, I have this topmost plot plane highlighted. Okay. I'm going to right click and I am going to add a trace. And instead of adding a trace associated with any of the things that we simulated, I'm going to type in our mathematical expression down here that we got, right? So if memory serves me correctly, it was negative 1.145. I'm going to multiply that by the exponential of negative, so now I need S1, so that was in my calculator as C, 11270.167 times time plus 0.145 times the exponential of negative, so that's like 88,000 something. Let me go back down here. 88,729.833 times time plus 1. So let's look at what just happened. The red curve, which represents the mathematical expression I typed in, just completely overlapped the green curve that was our simulated results for our inductor current. Since those two curves completely overlap each other, that means that our analytical solution that we came up with matches our simulation results, which must mean we did it correctly. That being said, there are a couple of caveat type things that we need to look at, okay? So notice what the range of currents over here on the left is. So we're ranging from 0.0 amps of current up to 1.0 amp of current. On the right-hand side here, because I typed this in as a unitless quantity, the right-hand side is the axis for the red curve. It's ranging from the same thing. It's ranging from 0 to 1. So I could make this look like I screwed up by simply changing this to range from 0 to 1.2. Now my curves don't match. And it's because the scales on both sides of the graph aren't the same. So we need to make sure that those scales are the same when we're doing our comparison. There's going to be times when you will do everything right, and then LT Spice is telling you you did it wrong. And it's because the scale size that it automatically puts on the right-hand side isn't the same as the scale on the left. So just edit the scale to make sure you're comparing apples to apples. So let me put this back on 1.0. Now let's put in our voltage just for the sake of argument. Although if we got the current right, it's practically impossible for us to have gotten the voltage wrong. So that's going to look like, was it positive 12.910? So add a trace. 12.910 multiplied by the exponential of negative 11,270.166 times time minus 12.910 multiplied by the exponential of negative 88,729.833 times time. And this greenish blue curve completely overlapped our original blue curve, so it means that our voltage expression was also correct. Just as a heads up, when I ask you to determine multiple quantities and all of that kind of stuff in your homeworks, which it'll be posted here in the next few minutes, I want you to use multiple plot planes like this so that it's very easy to read everything. Don't put everything on a single graph. That annoys the hell out of me. So just saying. All right, so class ended 2 minutes ago, so I am done. Good luck studying over the weekend and all that kind of stuff. I will probably pay a little bit of attention to my email. If you have any questions about anything, you can try to ask them. See you guys on Monday for your exam.
Question about 6. So when you redraw, like it says, use the ideal. So are we supposed to do it just like kind of like on 1.5, where you just redraw just the basic that we're just supposed to do it like that? So if there is like stuff in the way, I can on this one there's a voltage source and then there's 2 resistors.
Right, but so right here, you combine the 17 and the 500 into a 17.5. I'm on board with that.
Okay.
I'm not really on board with you ignoring the 3 milliohm, or excuse me, the 3 megohm resistor, but it doesn't do anything, so it's not hurting anything. So right here, this 10K and this 5K are in series, so why not?
15K.
Yeah, and then just do 3 volt in series with 15K, and now it looks like something you've seen before, and it should be very easy to do. So realistically, once you put those together, you could say, all right, so I have inputs on both sides. Okay, so actually do the analysis well. Yeah. So just lump those two together to make your life easier so that you only have to do KCL at this node and then.
Okay, so yeah, this is my other question. So even if we use the ideal, sometimes we're still gonna have to do analysis and not just use the equations that.
Right, because this one isn't, so this is like a type of differencing amplifier, but not all of the resistors are the same.
Yeah.
And so because we didn't see that, we have to do the analysis.
Okay.
Yeah.
And then this one's kind of the same thing where it's you have to do the analysis. Okay.
Absolutely. Coach, what else?
I got 2 questions.
Somebody, I've got 10 minutes before I have a meeting. Ask things.
For essentially that question. I did, I started off here with nobody had there, nobody, 6 hole, nobody had here. And you find the one I dropped is 270.
So I got a little bit of a problem with that, and what I mean by that is this 6 volts here is measured with respect to the ground, but that 3 volts is not measured with respect to ground because there's a resistor and this current is flowing through.
Oh, this is absolute ground.
Correct. So that's going to impact your results. So what you could do to make your life easier is combine this 10K and this 5K together because they're in series, and then that would put the 3 volt source connected to the ground. And then it would be 6 volts minus 3 volts over 15K is the current flowing that way. 6 volts minus V out over 17.5K is the current flowing that way, set it equal to each other and solve for V.
So after you do that, my question was, this, so is V out, which is not around, does this full node of V out as well?
Yes.
Okay.
But, so there's no current flowing through the 50 kilo ohm resistor, so V out is also that voltage right there. That's why.
Why is there no current?
There a closed current carrying path for the 50 kilo ohm resistor?
Oh, this is open?
But he said.
Certainly looks like an open circuit to me.
I thought it was implied wires.
No, there's no such thing as an implied wire. I want to be real clear about that.
Because if I have it like
This
this,
one,
plus
minus,
um,
are these, can this, so
if I have
from the inverting terminal and non-inverting terminal, the voltage potential has to be equal or the same.
Which means the voltage at this node right here has to be the same as the voltage at this node right here, whatever they happen to be.
So, but they're not both one.
I don't know.
Maybe over the square root of the.
It's either 4 or 0. Gotta
Times
be.
the vector.
But it can't,
1, 1.
can it be 0 though?
Unit vector.
Well, it's connected to ground, that's
So
the way I
what's
was
the
looking at
direction?
it. I had that same
The
question.
Y direction. In time.
Yeah, we'll have to look it up.
So you can always disconnect things and use a Thevenin equivalent circuit to figure out where voltages are going to be.
Yeah, I'll probably do that.
That answers one of mine. The other one was, for part, I got part A, part B, where it says how to change how the 20 ohm is hooked up.
Yeah.
Do you mean like this?
Yes.
Exactly like that?
But, no, not exactly like this, because you don't take away the resistor that was connected between the negative terminal and here.
Oh, I see.
Yeah. So we just add the 20 kilo ohm resistor on top, leaving everything else the same.
And there's still a wire that goes from here to here.
Go back to the original diagram. So is that a 20 K right there? Okay, so.
Yeah,
Oh, okay. I thought they wanted to disconnect it and
Nope.
reconnect.
So it's a completely separate 20 kilo ohm resistor that is wired across, tying those both together.
Okay.
Everything else stayed the same, just use that feedback path as well.
Yeah, I could say that.
Yeah, as you know.
If you have a differentiating amplifier and you have using your capacity, replacement there to become a integrated amplifier.
Yeah.
So I'm trying to figure out that 20K, I was just gonna simulate it, and just check that out.
I do, so I can represent
Do that, and then you, on my variable, because you don't have to. You didn't want it to saturate.
Right.
You know?
But,
I just drew one round,
Yeah.
connected the whole.
Yeah. Or you could just ground that part and then you draw one.
factor.
Yeah, we'll see on this one. I think I actually got.
where's the original circuit?
Yeah, crazy.
So I think I drew it like that, but this one. Well, now that I know that, I can. Now I got, I didn't know seven.
Why is it, she got a different one, dude. Yeah, I got it for free. Yeah. These things are like.
Yeah, wow.
Standard.
Yeah. The one with the handle.
Yeah.
What is about that?
They, they're not, my girlfriend, she's like, the sense of water, it's like the same thing. They're different, but hers don't lead to, the standing ones, they lead.
Well, that, because you're probably off by such a.
Send me this file, only take some time to look at it. I don't see anything obvious, but I want to play around with it.
To actually go through it, I just need.
Because I got to, I'm on the side.
No. Ideal models. Oh, it's negative.
So I was working your homework Sunday night, and I was gonna come to your office on Monday and have you look at what I was doing wrong, but you know what happens.
Yeah.
So this is homework 2, question 2. I don't know why this isn't negative. Because on here, it says negative 350 millivolts, or, yeah, millivolts. I'm not getting, just guessing, I'm doing nodal analysis.
He said.
Part A,
Yeah, part A, like,
this V1, 125 microvolts is connected to the inverting input terminal. So the 125 is supposed to be down here.
oh, so I have flipped.
Yep.
Okay,
Yep.
that makes sense.
You want the ASC?
Yeah, whatever the schematic file is, like, just tell it to
There's
stay.
like 4 of them in here.
Yeah, the ASC.
Right? What did you say?
Yep.
Okay, so for the homework, I haven't done homework 5, 6, or 7. I'm getting to where I can start doing stuff again about getting significantly tired. So like, should I just?
I
I'm
think
gonna
it would
study
be
it.
in your best interest to wait until after the break to take the test.
Okay, because
Yeah, because you miss and you're still catching up on the homework. If you try to take the test on Monday, it's going to go very, very poorly. And if you do it, have to use that trick. So I would wait until we come back. And
Okay.
study up and ask questions, all that kind of good stuff.
That
Don't
actually
shoot
makes
yourself
sense.
in the foot.
all right, I appreciate your generosity
Yep.
for your help, Dr. Hartman.
Mhm.
Oh, I'll email if you have any questions.
Sure thing.
Almost 5.
Okay.
I had a good call out. I assume it has to be like a 7-minute delay.
You do.
Or, but the issue doesn't know where to put it in the circuit.
I feel like.
So-
I did the homework.
Can I draw on this to explain something? All right, and this will answer your question as well. So if you're trying to find R out, take this guy out, find the open circuit voltage. That's gonna be your V Thevenin. Then short that, find the current flowing through the short. That's gonna be your I Norton, take the ratio of those two things, and that's gonna be your lowercase R out. Isaiah, you said something about the current being astronomically high. It might be correct.
No, because like.
Yeah, because that's not gonna be a real current flowing through anything. Yeah, so it's just what the math tells us if we had a short circuit.
I was just finding.
Yeah. Yeah, like there's so much.
Yeah. Yeah, so define later, so define the Thevenin voltage, you have to disconnect that load resistance. Because we're finding it with respect to the load resistance, and so whenever we're finding it with respect to a particular element, that element has to be taken out of the circuit. So find the open circuit voltage without that 8 kilo ohm resistor there, then short it, find the current flowing through the short, and the ratio of that open circuit voltage to that short circuit current is the resistance.
And then ideal voltage is probably on the ideal optic. I just want to test. And I have got this. Since I'm not.
That current zero, that current's zero. So that means that voltage right there is 2.5 volts, which means that voltage right there is 2.5 volts. This current plus this current must come together to equal 0. So that's gonna be 2.5 K over, there's gonna be 2.5 volts over 1 K plus 2.5 volts minus V out over 3 K is equal to 0, solve for V out. That's it. It's literally do it like we did in circuits 1, is what I mean by use the ideal optics rules.
What's that for?
Is this an example for that one? So that's what I have in my notes for ideal.
We were doing that to figure out what the value of RN would be and R out would be and ADOL would be for an ideal op. Then we put those numbers into this thing, solve stuff, and then you must have stopped writing down because I worked the circuit using the circuit one rules and got the exact same result, and then told you, don't do this ever again for an ideal op amp. Just use the circuits one stuff.
Okay.
Yeah,
That makes a lot.
yeah. Once we get to ideal op amps, it's supposed to be easy, not hard.
Okay. Efficiency.
Yeah.
We just.
Current flowing through the input terminal to zero, find the voltage at the non-inverting input terminal, apply that voltage to the input or inverting input terminal, KCL at the inverting input terminal, solve for the out. Which is, if you go to the lecture on common negative feedback circuits or whatever, that's the process I used to solve for the input-output relationship for literally every one of those circuits.
That's right.
So if you can't recognize what it is, that's what I'm expecting you to be able to do.
I think that's what I used for like finding what they were initially, because I didn't know what they would actually be.
Right near on the left.
Is it weird that 7 voltage over that 8 ohm resistor would be the same as our B out?
I don't know that it'll be the same, but it should be very close.
Okay.
Yeah, it should be slightly different, but it should be pretty damn close.
Talking about the
R out.
that one. So I forgot to do it the first time, and I was off by like millimeters.
Yeah, it's not going to be a large difference whatsoever. Yeah, which we shouldn't expect it to be, because that's why in the ideal case, putting a load resistor there doesn't actually impact it.
Okay.
Yeah. So if it's 9.89 volts, it might be like 9.91 volts or something like that. It's gonna be real small.
Actually, I think B out was almost the exact same.
Yeah. It may be real close. Yeah.
That can very like.
Well, make it give you more digits.
Formatting.
Yeah, just tell it to give you more digits.
Yeah, I couldn't tell the difference until I added more digits. Then I saw it. Didn't you say you had somewhere to be?
Yeah, and the student can wait for a minute or so. Hurry up. 6 volts. Well,
10 yeah, negative, positive. 6 minus 3, current flow this way. 3 over 15. Okay.
why are you doing 3 over 15? It shouldn't it be 6 minus 3 over 15? Oh, 6 minus 3 is 3. Okay.
That for 0.2 milliamps.
Okay.
Choose 0.2 milliamps goes here. There's no current
Yep.
flowing through there. These are in series, so this also over here should be 0.2 milliamps.
So 0.2 milliamps times 17.5 K plus 6 volts. 0.2 times 17.5. Don't do that crap, because the milli times the kill is going to cancel each other out. So 17.5 plus 6.
Plus 6. And why 6?
Because you have a 6 volt potential from here to ground.
Ground 6 volt potential.
That's literally what you have written there, isn't it?
Yes.
So I don't understand why you're saying why 6. You put it there.
Well, 0.2 milliamps. Times
So 0.2 milliamps times 17.5 kiloohms is the voltage dropped across this resistor. Got it?
Thank you.
Quickly.
I had a question on problem 3. It was finding this formula, and I was wondering if I did it wrong.
Did you get the right answer?
Well, I made an assumption
What assumption did you make?
that this VDOT is V out.
So I would define the current flowing through the inductor going from left to right, and so the voltage drop across the inductor would be from left to right, so that V out would be negative the inductor voltage drop, is how I personally would do it. I don't know what VDT is. It should be very, very similar to what we did with the capacitor circuits and all of that kind of stuff. So you're going to need to define explicitly the inductor current as well as the inductor voltage and tie things to that.
Okay, I thought that, current would flow from the left to the inductor, because you're saying,
If you choose to do it that way, that's fine. Where do you have VL and IL anywhere in this thing? Because
well, I was just using a formula. The formula for the current for an inductor is what? You're busy. Yeah.
so because we have lots of voltages and currents and all that kind of stuff, be meticulous in your labeling. So if you're talking about inductor currents, label it with a sub L, inductor voltage, label it with sub L, so that we can easily track down things and all of that kind of good stuff. Again, derivation should be wildly similar to what we did in class when we were doing the common negative feedback topologies. So go back through my video and look at when we derive the different drive relationships for differentiator and an integrator. It's going to be really, really similar to one of those, except that the inductor is being replaced by a capacitor. Or excuse me, the capacitor in the lecture video is being replaced by that inductor.
Thank you.
And just as a heads up, I don't remember right off the top of my head, but I think with the capacitor right there, we wound up with an integrator, which means we should wind up with a differentiator with the inductor. So it should be the opposite calculus function if you swap the capacitor with the inductor.